Thank you, Filip.
Thank you very much. Thank you for coming here. Good afternoon. My name is Filip. I do offensive security. I'll talk to you about hardware security in particular today. So who am I? I'm a lead pen tester. I'm a red teamer. I love doing physical security, but a little disclaimer here, I don't do it professionally. I do it in my own time. And this presentation is something I've come up and reproduced as well during my university courses, and this particular topic is something I wanna pursue during my PhD. In my free time, I'm also a fencer and photographer. I'm also interested in physical security, such as lockpicking, bypassing, any weird stuff you can find in buildings. So let's go into the lecture. Why am I doing hardware? Why do I like hardware? Well, it's awesome. It's pretty neat to just destroy something or just like tear it up apart and see what's inside, see how it works, how things that are maybe everyday use, like smart homes, everything smart, like bulbs, etc. How do they work? Since we don't really think about it every day. It's also not that popular. Pen testing hardware things. It is somewhat popular, but not that really. Mainly, if you think about security, you think about software, red teaming, application pen testing, etc. There's a lot of it. Every single store you go to, you can find at least like 10 different smart stuff which you can buy pretty cheap. Take it home, tear it apart, see what's up with it, maybe hack it, and have a lot of fun. And if you like tinkering, that it's like the perfect thing you can go for if you also love security. So, what do you use for fault injection? I use personally Chip Whisperer, which is on the left here. It's a low-cost device from New Way Technology, designed by Colin O'Flynn, which is a great resource for studying hardware security, especially fault injection and side channel analysis. It's low cost. It's not that low cost. It's about $250, but comparing to other solutions with fault injection, it's pretty cheap because commercial solutions for fault injection can go up to tens of thousands of dollars, depending on what type of injection you do. You can also do for simple fault injections, for like voltage fault injection, clock injection. You can use the FPGA. For clock injection, you can also do it with Arduino. These are also low cost, although FPGA might be a bit more expensive, but it's all depending what do you want to do, what's your background. If you're like an electrical engineer, then FPGA might be for you because you might be familiar with it. Chip Whisperer is my choice because first, it's cheap, it has a great community to it, and everything you write for Chip Whisperer is written in Python. It has an API, so you can just do it pretty easy, although it might be still weird if you don't know what's the fault injection about, what's side channel analysis, and what you're trying to accomplish. You also need an oscilloscope, which is pretty good to have. Although Chip Whisperer has its own oscilloscope built in, it's way easier to visualize things using standard oscilloscope. Obviously, a soldering iron is good because you have to pretty much tear it all apart all the time, connect stuff to it, and you can't do it without soldering, or maybe you can. I doubt it. So what is fault injection? Definition by ChatGPT. It's a method used to test how well electronic systems can handle unexpected problems. It's also called glitching, which I think everyone is familiar with. Like glitching in games, for example, speedruns, you do some unexpected stuff to skip some time or force a software to behave in an irrational way. So this is what we do with fault injection. but we have a bit, we're aiming for a different outcome in hardware. So the first type of fault injection is clock glitching, where you glitch a clock, which every device, devices will rely upon to execute instructions. So on the left, you have a regular clock cycle, which is used to load and execute instructions on each clock cycle. What we do with glitching on the right, we're trying to inject some clock pulses in a very maybe irregular way or very particular way, depending on what we're trying to do, which will cause device to behave irrationally, maybe skip instructions. This is what we might be aiming for, to skip instructions. So the first, very simple example of clock glitching would be a simple nested for loop, which always has to print 2500. But when we start introducing different clock cycles, we see that the results are somewhat weird and the device doesn't do what it's supposed to do. So this is a very simple explanation of what fault injection does. The next one will be voltage glitching, which is a bit more different. I think it's mostly utilized to perform glitching attacks because it's way easier. I mean, it's more finicky, but power lines in a device are always accessible. You don't need to worry about if the device uses an external clock or what does it do. Power lines are always there. But it might also cause some issues because what voltage glitching does, it's just lowering voltage for some period of time, and to find that sweet spot where the device doesn't do what it's supposed to do. So you're gonna have a lot of reboots depending on the target. If the target comes up a long time after the reboot, this will be very slow, but it's more finicky as well, because if you use cables, like different lengths of cables, different types of cables work, will leave you with different parameters to successfully exploit the glitch. So if you change cables from 20 centimeters to 30 centimeters, the parameters will shift, and you're going to have to find the glitch point once again. But it also can glitch devices which do not work synchronously with a clock. So this is, I think this is the most popular type of fault injection. I've been seeing it a lot, and this is the type of fault injection I will be showing in the case study later. So what do we use fault injection for? It has some pretty neat uses, like secure boot bypass. I've seen a paper where the researchers bypassed secure boot mechanism using laser-induced fault injection. So like they used very precise laser to induce glitches in the chip, and they successfully bypassed secure boot, which is pretty interesting use. I think secure boot bypass is very interesting. Doing authentication bypass, imagine some device that works with pin authentication. You can try to inject glitches where when the authentication check happens, and try to skip that instruction so it does not check for it or returns a positive outcome for you. Getting access to locked functionality. This is something we will do today. It's something between authentication bypass and getting access to locked functionality, because we'll be unlocking a debugging mode on a STM chip. JTAG authentication, JTAG is a debugging protocol. It can use authentication, and it's widely used. the fault injection is widely used to bypass that authentication and get a debugging session on the device. It's also used to recover keys, cryptographic secrets, which I will show you an example, which is not mine, but a person did it in a very, very special way, which is kind of awesome if you think about it. So what's the types of fault injection? How do we do fault injection? We can do differential fault analysis, which is getting a lot of inputs and outputs from a correctly running software, and compare it with everything we do with a fault, with the results we are getting after we inject faults, and then differentiate it and try to recover the secret. Bear in mind, this is also all with extracting secrets, these three methods. The next one is collision, which we try to get a lot of the same results, then get a faulty outputs and analyze that to obtain secrets. The last one is statistical fault analysis, which is getting as many faulty outputs as we can, and then use mathematical analysis to try to obtain the secrets. So I'm going to show you an example of recovering secrets. I mean, there's no example, but this is just how what someone named Stefan Filipek did. He used a camera flash, optical fault injection method to recover on an Atmega chip. He ran a simple AES encryption on the Atmega chip, and then just pointed a camera flash, his Nikon, because Nikon particularly has a functionality where it can blast flash constantly, almost constantly, which caused the chip to malfunction and in the end recover the encryption key, which is very neat and something you wouldn't really expect to perform with a simple camera flash. But this is something which some researchers do in a very expensive environment, because laser, EMF, it can become quite expensive to research. The hardware to do it is really expensive. Okay, so after explaining to you basically what a fault injection is, I'll show you a quick study on Trezor One. Trezor One fault injection has been widely described pretty much everywhere. I think most of you have seen Joe Grand on YouTube, who exploited the fault injection in Trezor One and recovered like hundreds of thousands of dollars in cryptocurrency. Unfortunately and fortunately, the Trezor One is now patched, so if you perform the fault injection, it's still possible, but you won't get access to the secrets, the seed, which will allow you to recover access to your device. But it's still possible by design. It's running on STM32 Cortex, and also Trezor One is open hardware, which is great for you to research because you have access to everything. You have PCB designs. You can basically do one yourself if you have resources. So everything is there. Also the firmware is also open. You can download it on GitHub. So why the fault injection allowed someone to get access to seed with fault injection? Because at boot time there was a moment where secrets were copied to SRAM, and then you could, if you had debugging session on the STM32, you could read the memory and extract the secret then. So how do you inject faults into the STM? So STM32 has an internal voltage regulator, which is directly connected to memory and kernel. It also has two capacitors, on the way to the voltage regulator. So this is where you would be. This is your target. This is where we're going to inject faults. So what's the deal with, what are we trying to do with this fault injection? STM32 has a readout protection, which on level 0 is everything is open, you can read every section of a memory. On level 1, you have some access to the memory, and on when the level 2 is introduced, it's actually impossible to go back to level 0. So this is basically if you're doing development, you're doing it on level 0. If you're shipping the device to the masses, you're introducing level 2. So all the things are secure in theory. So this is the PCB of Trezor One wallet. I don't think you can see that. Oh, no, it's not. So we are going to. Can I have a laser pointer, maybe? No, you don't have one? No? Oh, okay, that's fine. So in the left top corner of the chip, there's a VCAP line. There's a few, oh no, sorry, I have it right here, sorry. This will be better. So somewhere here, these are the 3 capacitors you need to unsolder, so you won't have voltage regulation. So the capacitors are regulating the voltage. So if some differences in voltage occur in the runtime, the voltage will be stabilized. So we don't want that in fault injection, in voltage fault injection. We want it to be as pure as we wanted. And the line here is a VCAP line. The capacitor goes from here to here, and this is a VCAP line. This is where we want to inject our faults. It's okay, thank you. So preparing the Trezor One to the attack, I'm telling you this red piece of wire was so much fun to solder. It was like 0.5 millimeter maximum. It took me like 2 Trezor wallets to do this. But fortunately, I bought like 5 of them for $20 on all of them were used. I also hoped for some crypto wallets on being there, but unfortunately, I'm not rich now. So maybe the one I broke had it, but no, I didn't get any money from it. So you practically connect all of the cables to the debugging ports. There's a reset line as well, which will act as our trigger. And the red wire is where the attack is being performed, where the glitch is happening. So after connecting everything to Chip Whisperer, we get something like this. We also use ST-Link. It's STM32 debugger, which will check if the Trezor wallet debugging has level 1. We're aiming for level 1 readout protection. Basically, if the device is in level 2 RDP, if you connect the ST-Link to it and try to connect the debugger, it won't work. The light will be red all the time, and you're just not going to have any connection. Basically, the setup is like this. We have from Chip Whisperer, we have FPGA target and prog reset. It's these are the Trezor One reset lines will tell the Chip Whisperer when the chip is when to reset it. I mean, Chip Whisperer will reset the device. It's gonna happen like that. The glitch is gonna happen. Then the Chip Whisperer will check with ST-Link if the debugging connection has been established. If it has been established, then great, that's it. If it hasn't been established, then Chip Whisperer sends a reset signal, it resets the Trezor One and does it all over again. And this was a long process. This takes a lot of time. I apologize for a screenshot in Polish, but This is how the boot sequence works in Trezor Wallet. So basically, the yellow line is the RST line, and when the RST line becomes high, the boot process begins, and about 160 microseconds after that, after the reset line becoming high, the flash is red. So this is basically when we are going to do our glitch, about 160 microseconds. And with glitch loops, we're gonna check the range of 140 microseconds to 170 microseconds. Basically, because we might have some different stuff going on. We don't know where the glitch is actually going to happen. So we try a lot of parameters, and the boot mode enable function just checks if the debugging connection has been established. And there's a gimmick with the ST-Link, because if you use ST-Link is also connected to your PC, your Raspberry Pi, and whatever you're doing your attack on. And apparently, if you try connecting the debugger once and it fails, you need to reset your Raspberry Pi or your PC USB connection, because it will just, if you have successful debugging connection, it will not detect it. You have to reset the USB every single time you try. So this took me about a week to get, because I had no idea. I've ran glitches for a week and didn't get it. Someone mentioned it on the internet, so I was very grateful for that. So this is a glitch, basically. This is how it looks. This is the external offset of 0. So basically, when do we do it? The external offset 0 should be where our trigger line is RST becoming 1, so the green line becoming about 3 volts, 3 volts. This should be when the glitch is happening. As we see, the glitch is happening before that, so we have to make the difference. So the difference is about 20 microseconds, so the final will be around 180, something like that. So doing this, we got the offset of 197 microseconds and some rest, where the glitch is successful and the connection is established. So basically, on the below screen, you can see that OpenChip debugger, you have a connection and you can dump the memory. So in the memory, we try to confirm that we have actually dumped the memory. So we're looking for a string which is listed on the GitHub in a Trezor firmware repository, and there's a structure, there's a WinUSB string, there is a WinUSB string in our dump, so this is successful dump. With the unpatched version, you will look for seed, so you would look for different structure in the memory. Unfortunately, this is patched, so no cookie. So the end is the quick demo, which is how the attack actually looks like. And the bottom is the terminal. So I hope this is well seen. Can you play it? Yes. And you will see that ST-Link becomes green when the glitch is happening, and you can basically now read memory, which would be impossible when the level 2 is introduced. So this is it. Thank you very much. It's a bit shorter presentation than I anticipated, but I hope you enjoyed it.